the next and the last presentation. It's deep learning tools for automatic diagnosis of rotating electrical machines via vibration signals, and it will be presented by José Enrique Ruiz-Sarrio, postdoc researcher at Polytechnic University of Valencia, Spain. He's, and again, I'm quite proud to say that he is also a graduate PhD of our university in the frame of a Marie Curie project. So,
okay. Thank you for the kind introduction. I was not that brilliant as a student, I must say. So, first of all, I'll give you a bit of context about this presentation. It's a bit different from what we have seen today. It's not, let's say, a magister lecture like research sharing. When Claudia told us, okay, we are going to have a training event in the frame of the project, and it's going to be a workshop. So we thought, okay, so let's share some knowledge, but some basic knowledge. For who? For those that didn't use AI in their whole life. So I know that some of the room today, you will be, okay, this is really like the basics. We already know how to do this, but we conceived this presentation to give these first steps to these ones that they never used it. So just to provide you a bit of context about the presentation. Okay, so first of all, I will have to add some words about the research group which I belong to, together with my colleagues here. We are part of the Institute for Electrical Technology within Universidad de Valencia. So some few words about this group. We belong to the Advanced Diagnosis of Electric Motors and Generations team within the Institute for Electrical Technology, which at the same time is within Universidad Politécnica, so it's the structure, right? The group head is Professor José Alfonso Antonino Daviu, who is not present here in person. This is some facts of the group. And now I will speak about myself. It's not required. Claudia already told you about, so I will carry on. I will just say that I am not an artificial intelligence engineer. So I am an electrical engineer. I work a lot with motors. Basically, my main research interest right now is to apply high frequency electromagnetic phenomena to detect faults in machines and most importantly to diagnose them. So this is about me. This is as Claudia commented briefly. And this is the applications of this workshop that we are going to see today, right? Most importantly, what is my main goal today is not to teach you anything about AI itself. Of course, I will use it. But my main goal today is that you understand the workflow that us, as let's say, maintenance engineers for electrical machinery use to detect faults online using this kind of techniques. So this is my main goal today. And I want you to have this scheme in your head. So as we saw already many times today, we acquire the data, we process it, and then offline, we do organization, we select an architecture that we like or performs good for our intentions. Then we train this architecture and we validate this architecture. When we have the validation, the ideal thing that I will not cover today is to implement it in an embedded system, which has enough computational capabilities to online monitor the status of the rotating machinery and automatically diagnose the aging, faults, etc., etc. So this is my main aim today. And okay, let's get started with the real content, right? So some basics about maintenance engineering applied to rotating machines, right? So this is a really nice pie chart that is from a paper that you can see there in the bottom. And here is the different faults that you can find in rotating machinery depending if it's low voltage or high voltage. And this is the main distinction here, right? As you see, 41% in low voltage machines, which are the most common in industry. We have most of these than the others, right? Are in the bearings. So today I want to focus on this. What else? Predictive maintenance. We spoke before about this today. But I want to give you another perspective about predictive maintenance. So what is it? At the end of the story, is it a cost-effective solution to industry? Why? Let's see why, more in detail. So I am the maintenance manager in this company. We have a large fleet of motors. And when should I perform maintenance? Every day, every week, every month? We don't know. So for evaluating this, I would say there is two approaches. One is periodically, so every month, every week, every day, every hour. And another option is, okay, when alarm is triggered, so when we have a system that gives us an alarm, okay, hey, look at me, I'm failing. This is not working properly. And how do we evaluate when we have to take action? So we base our decision in two main factors, which is the system initial investment. So me as a manager, when I have to spend my money, on how much, and the other is how much do I have to spend to perform this maintenance. So if we look at the periodical inspection or periodical maintenance, at the beginning we don't have to spend so much. We just have to have some equipment, some personnel to do it, okay. But if we want to have a system that triggers alarms, it's a more fancy equipment with more sensors, fancier processing units, etc. But on the other hand, the cost of operation of this is way higher. Why? Because if I have a motor in my plant, in my industry, and I want to perform maintenance action, I have to disassemble it, I have to take it to the workshop, perform the several inspections, several tests to see where the failure is, so on. On the other hand, if we have an alarm, we don't have to perform as much tests, and we have this fancy equipment that says, okay, it's a failure, most likely coming from here and from there, okay, and this is a big discussion. But this is the main aspect behind predictive maintenance. What else? When we have it periodically, we call it time-based, and we have it. When an alarm is triggered, it's called condition-based, and the condition-based itself is what we call predictive maintenance. Then we have the ultimate challenge in our field, which is the prognosis, or to be able to forecast when a failure will happen, depending on several factors that you can measure and you can quantify. And this is, let's say, the basics that I wanted to establish, the ground floor. Now, artificial intelligence, how can we use this? Okay, for some of you, maybe evident, right? But when I was in my place doing this workshop, okay, maybe we can hire a robot for me in the workshop. It would be funny, right? Same, but even more funny was the idea of a motor with hands and legs that repairs itself, right? Okay, this is not quite like this, obviously. But artificial intelligence can definitively help, for example, to generate these images. I had a lot of fun doing this. But okay, for real, how can it help? So we do automatic diagnosis using AI, mostly machine learning and deep learning. I will not go into the difference of it because we saw it at least 4 times today. But okay, I will leave you with this picture, and I will leave you here with some recommended reading that I enjoyed it. It's some of my favorite articles on this matter. One of these, this one from 2015, the one from Nature. It's called Deep Learning, and it's a short paper for some Facebook and engineers. It's really interesting. Okay, let's carry on. So we have the ground. Let's go in the process. First of all, if you remember, data acquisition. And for this workshop, it was intended to be a hands-on workshop. I'm going to use a data set, which is open source. So first of all, most important step is this, data acquisition. Why? As we already saw again today, bad data, bad decisions. So data is the most important step. Now, what am I going to use for this workshop is signals from it's a well-known data set from the University of Paderborn in Germany, where they have bearing fault data. So bearing fault classified on healthy state, inner race fault, and other race fault. Here you can read some of the characteristics of the data set, which is one of the most important aspects to understand here. So it's one of the most important aspects to understand. So what they did here is that they have this data. Let me show it to you. So they have this kind of setup with a motor. They have a measuring stab with some speed and torque sensors, and they have a bearing module with a bearing and a radial force. I think it's a spring. It's kind of a spring system, right? And then they have the load motor to perform some different operating modes. And then what did they measure? So they measure the current and the voltage of the normal motor. They measure the speed and the torque in the measuring stab, and then they measure acceleration surface acceleration, they measure the radial force that they apply, and they measure the temperature. Anyway, in this workshop or in this presentation, we only care about the vibration. Here you have a from the paper, okay? And what else? They have a set of data. Then we'll have a look how it does look like in real life. But they have a lot of data stored there in their system, and you can download it. But this data is structured in, let's say they have a code. So the first thing I would like to do is to explain this code. So the first thing is KA01 is what they use for identifying the bearing and the healthy state. This is faulty, where, how. Then the other number is the applied radial force, and then we have the torque and the speed. For example, just to give you a hint, N15 equals speed 1K500 RPM, and torque is Newton per meter, etc. You will see now when we carry on with the presentation how they structure it. But basically, they structure the data on healthy bearings, artificially damaged bearings, and accelerated lifetime bearings. So they are classified in different ways. Let's have a look at this. So most of you know how a rolling bearing looks like, right? It's a common device used in all rotating machinery. And I would like to emphasize that due to the limited extent of, let's say, because it was intended to be a workshop, so I didn't want to put a really big amount of data, so I'm going to only work with the artificial damage, right? So only with bearings that were artificially damaged. How did they damage these bearings? Let's have a look at it. So the mesh that they implemented is like just drilling on the outer race of the bearing. The second type of damage that they implement is some electric discharge machining, which is like a common bearing fault in industry. But in this case, they just perform like some electric discharges to do how you call it, like just an empty space in the outer race. And then the other fault that they implemented is this artificial pitting by using an electric engraver, like really like artificially made. Like we can all in our workshop at home do this with some equipment. It's not really fancy. But okay, they did this and they measured these bearings. They acquired all these signals under these circumstances. Here you can see, for example, how they classify the bearings, where the damage is done, right? Or in the outer race or in the inner race. Different damage extents, so more damage, less damage. They just say 1 and 2. Okay? So 2 millimeters, no, just 1 and 2. And then how they perform, depending on the code. Okay. So now we have our data explained. We know how they acquired it. We know how they damaged the bearing. So we know that up to some extent it's a real damage. And now let's see how the data set looks like, right? Because we go to this page of Paderborn, we have a lot of folders, we have a lot of data there together. But okay, I saved you some time and I organized it. So this is how the data looks in my computer once you download it. As I said, I am really doing this for giving people that has zero AI knowledge of how to do these first steps. So this is how the data look like in folders. And what is inside this folder? So you can see the bearing codes. So inside each bearing code, we have these MATLAB structures. And as you can see, each MATLAB structure is for one operating point and for one bearing. And in the top of that, as you could, if you pay attention to the first slide, they perform 20 measurements. Just the same measurement. Same operating conditions, same bearing, 20 measurements. And this is how they organize the data. So let's go deeper in this data. How does it look like? Okay, I open my MATLAB software, I load it, and this is what it is. So information, general information, x-axis depending on the resolution of each signal, y-axis, and then this is where we want to look at, right? Y-axis. What is inside this y-axis? Here we can, as you can imagine from the previous slide, force, phase current 1, phase current 2, speed, temperature, torque, vibration. For this workshop or for this presentation, where do we want to look at? As I told you, on the vibration. Okay, here you have some current that is coming over time. And this is our data. This is what we are going to work with. Now, once we know our data and we know how our data looks like, let's go to the AI. So we want to apply deep learning techniques to this, and now we can discuss more on which technique is better for this purpose, which advantages and disadvantages. But what I want to do here is that you guys, or some people wanted to apply this technique, transform the signals into images, because we are going to apply convolutional neural networks to discriminate between images, right? So this is my creation, right? I invented it myself. It's not anything fancy, as you will see. But okay, how do I go from vibration to image? A priori is not immediate. Okay, the fact is, of respect. How do we do this? So sky's the limit. There is many ways to transform signals into images. Imagination is limitless. So I selected an easy way, but really in our group, there is people, Vicente, for example, applies different technique to the same purpose, other colleagues apply other techniques for the same purpose. So it's really like you go find papers, there's papers about a lot of these things. So it's really a creative aspect, as everything in AI actually. So for this workshop, I want to use a simple time frequency transform as STFT, right? For those not so familiar with this, I will tell you that this is an improvement to the fast Fourier transform when a priori we don't have steady state signals. So I will go through how this STFT looks like. For those that are used to work with signal processing tools, this will not be anything fancy, but those who are not experienced with it, you're welcome. So I use a very simple function, which is a spectrogram in MATLAB. It's really in MATLAB because, okay, we get the data in MATLAB, why change? Why go to Python? We stay in MATLAB. So a spectrogram function, what is this? We have output input, MATLAB function, right? So what do we have inside here? Output, we have an S matrix containing the spectrogram itself, so the numerical value in two dimensions. And then we have two vectors, one frequency and one with the time range. For obtaining this, we need the signal to be transformed in time domain, right? The X. The window, so what is the window? The window is what performs the STFT, because we have the signal, and now what we want is to window the signal into many little windows and perform the fast Fourier transform in every little window. How does this look like? Like this. So we have this window. Now we perform the FFT on this window, and we'll have a certain representation in two dimensions. So what else? Overlap. So we have a window, but we also have an overlap between two consecutive windows. And this is, of course, it's a tunable parameter. Depends on your interest. What else we have? An FFT is a parameter that tells you the number of samples that your Fourier transform has inside each window. And you also have the sampling frequency of your sensors or your acquisition system. And the STFT is performed one window after the other, and so on. So, of course, it's not perfect. It has some drawbacks from the signal processing perspective. So we have, I don't know if you heard about this Heisenberg uncertainty principle. We cannot say that we have these frequencies in this time, right? Because we are doing a time window. So let's say it's an approximation. But okay, we do it and we deal with that problem. And we know it. But then there is another problem. There is the problem of resolution. So this is the main problem of STFT. And that's why in many applications we have to use more fancy tools. It's because we can only select or the frequency resolution or the time resolution. Not both. So if you want a thinner frequency resolution, you sacrifice time resolution and vice versa. And this is the main drawback of this. But anyway, as I said, for this workshop, for learning how to perform this kind of techniques applied to this data, it's a valid solution. And my objective was to basically create kind of like a barcode signal, right? Because we have a steady state signal. So if we perform like a kind of a barcode image, we can differentiate between different signals. Maybe, right? We don't know. So some code for those interested on really like doing this manually and so. Just a few words, this is some tunable parameters. I take a long window size because I want like more frequency resolution than time resolution, but as I said, the sky is the limit, try your own and do as it better perform for you the application. We have the spectrogram function that we commented, and then we have this windowing you say, okay, with this windowing. This windowing, just between you and me, just really easy explanation is that improves the transform quality. I will not go deeper like with the intersection between the two signals and the FFT basics, but okay, just please, if you want to do it at home, put the window, you will tell me later. What else? Then, as I said, these are already mentioned, and what we want now for, as you will see later, for our architecture, we want 2024 per 2024 pixels in our image. So how do we do this with these two functions? And in the top of that, I was thinking, okay, maybe I want this data set that I stored as an image to be as small as possible. So instead of using a RGB channel, which is 3 channels, I'll use black and white, which is just 1. So I reduce the size of the data. So that's what I did. I did first adjust the resolution 2024 by 2024, and then I put it in like grayscale, which is from 0 to 1 maybe the method. Okay, we have our images. What now? So here you can see, I will zoom it in. Here, well, you see the codes. I put it just in case, just to have a reference. So this is the same signal, just measured at different times. Just I take one measurement, take another, take another. I don't know if you can see some difference. I see some differences. What else? Here you can see now 4 different operating points for the same bearing, but different operating points. You see a bit more. You see I don't think you can differentiate a pattern. Of course, it's only 2 samples. And basically, and then this is the same operating point, but different bearing fault. So this, in my opinion, should be more different. But this, I'm just showing you these images to prove that. Can you see any pattern? I don't think even if I show you 1,000 images, you could see instantaneously any pattern using this method. Exactly. But you know who knows? This guy. So we have our data and we have our data label. Which kind of learning is this? Supervised and supervised? For those that you are not familiar with the artificial intelligence, maybe now you better know what this kind of learning is. So it's supervised learning, I would say. And now let's go in the artificial intelligence part. Okay, let's see what we do. And at first, I wanted to show you this super cool video, if I can do it. I want to show you because it's not running because I need internet connection. In the test that we did, it was running. But okay, I will give you the link. It's just a very nice. I let the guys that know about this topic to explain it, and it's like a 1 minute just how convolutional networks work. So how the different features are, how do you do the max pooling to reduce the dimensionality, and so on, till you arrive to a fully connected layer that classifies. Because I don't remember if I mentioned it, but we are performing classification tasks. So we want this algorithm to tell us if it's healthy, if it's inner race fault, or if it's outer race fault. So what else? As you saw also in previous presentations, we have different layers, and its architecture is singular. How many architectures can you use? Also endless. In this case, I used GoogleNet because it was easy to access, and as you will see, it's really accessible. Like you just click on the application, download it, and utilize it. Here you can see another examples of architectures, but anyway, here you have a wide variety, so it's up to you. Okay, first of all, since I selected this architecture, I saw the necessity to explain a bit what is inside. So let's have a look at the top part. So as you can see, this is the whole architecture, right? Starting from top to bottom. Let me pass it forward. So this is the whole architecture. And we are going to zoom in just some parts, okay? Later you will see which application I'm using, because I'm using a very user-friendly UI application that is available in the app. So you have output, and we start with the first convolution. First convolutions, then nonlinear functions, then pooling. The pooling is actually quite utilizing this kind of convolutional neural networks to reduce the dimensionality one time, another time, and so on until you have like a very small dimensionality. So particularities of this Google Net is this called inception models. Basically, what they thought and the main idea behind this, is to have different resolutions. So they have 4 branches in parallel, and this have like 3x3 convolutions, 5x5 convolutions, 3.3 with max pooling, and 1. So different resolutions. So their idea is that, okay, like this, we can generalize more, or we can like say differentiate better from image to image. Just say this is not commonly used for diagnosis. This is used for image recognition way. Let's say it's a way more fancy task than the one that we are performing today. But this is open source and it's easily accessible, but also. And at the bottom, at the end of the story, the most important point here is that we will use this fully connected layer that just outputs the classification. And that's the main point that you have to grab if you don't have any idea of AI. Also, what should we input to this? Because I said that I transform my images into 2024 per 2024 pixel images, and I set it in black and white, and surprise, it has to be RGB. But okay, I didn't care about it because at the end of the story, my intention was to reduce the size of the data to store it. Okay, I just transform it again, and problem solved. So now, dividing the data, because we are going to train the network. As we already saw, again before, we have to divide the data into training and test. In this case, I perform it a bit randomly. Of course, I supervise it, and okay, if you give me 1% of test data and 99% of validation of training data, it's not okay, right? So it's random, but it makes sense. And now I use this GUI application, which really, if you don't have any idea on how to use AI, this is the first necessary step. It's really easy to use. It's a GUI, as you will see now, and it's really easy to implement every architecture, input the data, have examples, samples randomly selected. You will see, it's really, really nice. So this is how the application looks like. You can see here we have our architecture. This is a snapshot of what I saw before. And we have three tabs, right? Designer, data, and training. Let's see what it starts. Okay. Here you can see the first training tab. And just to give here, we only use the training data, right? We separated the data. Here is only training. So we have different settings. But I just want to mention here, if you can read these augmentation options. What's that? Right? So what is augmentation? Normally, when we have a set of data, we can say, okay, look, but if you have data and you try to fit the data, it's going to be what we know as overfitting, right? So there is some techniques that can easily avoid this overfitting, and it's called data augmentation. Basically, what we do is like they do some slides, some tuning, like really easy operations on the images to generalize better the data. And this is what they call data augmentation. In my opinion, if you want to use this kind of approach, this is better to do manually because each process has their own features and each process has their own, let's say, outliers. So I like to do this manually, but okay, since we are using the applications, we did it like this. And then we have this validation tab. This validation tab is inside the training data. We have training and validations for the back loop. So again, but this is done automatically by this application. You have to select a percentage of the data to be used for validation in the training process. Okay. So once we are here, we have to input our data. Let's see how it looks like. So you see, training data by class, we already have our folders with healthy inner arrays, outer arrays. So here is just how the randomly selected data is distributed into training and validation data. Here you can see also some random observations of all classes. Okay, fine. Just saying this is just by chance that more or less the distribution between classes are the same, just by chance when I perform this analysis. Okay, so we have our data, training. How does the training look like in such application? So, yes, I will go fast through this. Okay, at the end, training is to tune weights and bias, right, of the similarity. So this is the big concept behind it. It was already explained at least 2 times today, so I will go forward. Okay, So we have our solver settings, which has many options. I will not go all over them, but just saying that the most important ones, in my opinion, because some opinions sometimes is the mini batch size that we will see what is it, and the learning rate. This is the two settings that you must look at and really influence your training process. What else? The data strength. This took me 4 hours and a half, but here I'm showing you the output. Okay. First of all, blue graph is accuracy. Orange graph is loss. We already also saw this today. So loss, how much deviated we are from the truth, right? And accuracy is the same in another words, in my opinion. So I would like to clarify now some concepts, and I put a lot of text. So hold on. Let's here overlap. So this mini batch, when I first saw it in this application, mini batch, it's a batch, right? But it's a bit ambiguous concept. So if you go to Stack Overflow, for example, which is a limitless source of information about programming, you will have different. At the end, it's the same. Then what is a batch? A batch is just the data that goes in one pass to your neural network. But then inside that, okay. And then what defines an iteration? What defines an epoch? Because it's also really training parameters that you don't see anywhere else. So an iteration is one time the data going in your data and going forward and going back. And an epoch is when the data set sees all the data that you input, all the data. Because an iteration maybe not be all the data, maybe a mini batch that you define the size yourself. This is the concept that must be clarified when you do this kind of training, in my opinion. So we have our neural network that at the end of the story, it's a .mat file, which is like a little tiny box that is able to make predictions. So what do we do now? We have to, okay, how accurate is this? Right? We trained it, but is it really working? So we take the data that we separated before, that we didn't use for the training, and we perform some kind of validation. So, as I told you, randomly selected for the 3 classes, healthy, inner race, and outer race. And we use these confusion-matic techniques that also made some mention in the previous presentation. So we already know how to read it, right? But okay, for our neural network, we see that okay, more or less coincides with the training parameter, like 90-something% of accuracy. Not bad. How can we implement this confusion matrix? Also, I give you here a piece of code that you can use in MATLAB. It's really easy, right? This is for obtaining it in percentage. And okay, we are at the end of our training process. We have our little tiny box that can tell us if we have an outer race fault, an inner race fault, or if the bearing is just fine. So, once we have that, what now? We already spoke today about embedded systems, about processors, and so on. So our objective as a maintenance engineer is to have a little tiny box with this train box that tells us, hey, look at me, I have a fault, or I may have a fault automatically without me taking any action. And this is challenging, right? Because, okay, we can have false positives, that's clear, it's not a perfect system. But then also it's a really complex system. For example, this Google network, in my opinion, for this purpose, may be too complex, right? So at the end of the story, when we look from the maintenance perspective, we have to consider this big trade-off, complexity and feasibility for all purposes. And this is quite tricky. And then, of course, there is also the belief and the truth that if you train a system with this limited data, you cannot extrapolate it to anything else. And we all will agree that if I perform this, if I train this data with this bearing data, I cannot go and use another model of bearing and pretend that this application works. So this is things to have into account. Okay, as I said, another closure that I like to point is signal to image, endless possibilities. So really, a lot of ways. Maybe some doesn't work, in my experience, and some perform better than the one that I explained today. So here you can write a paper based on this if you want. Okay, and now a final reflection, a kind of a problematic. Okay, we have our data acquisition, We have the pre-processing stage, we have the selection of the architecture and the training and so on. And then we have this accuracy versus computational model. And I always like to see it from this perspective, personally. Maybe for me, this is not so clear. I will not include this, I will not include that. But for me, this really sums up the whole thing applied to the maintenance. So if I want to do this in my industry, because I am the maintenance manager, I would like to know, okay, but how accurate is this? Or hey, how much knowledge we need to this? Do I need to hire an AI expert? Or hey, how much do I have to invest in sensing or stuff like that? So to take away, to go for dinner later, and I leave you in peace. Okay, online automatic diagnosis is just to assist on predictive maintenance for relative dimension. And I like to insist on this online, right? Because at the end is the ideal system. You have your box in your motor that acquires signals and triggers you the alarm. This is again the architecture, sorry. Replying the same word a lot of times. The process that I wanted you to keep in mind, right? And then, okay. Of course, we are using deep learning here, so don't pretend to use a technique like this and to be able to recognize something, because the main aim, in my opinion, of these deep learning tools is to see things that we cannot see, or to detect things that we could not detect in any other way. Other thing, be careful, beware, because if the training that you use, the data that you use is not realistic or is poorly processed, this is useless. And yeah, I like always to say this, and I learned it actually in Siemens from my previous supervisor from Fabian. Some of you may know him. This is AI, so there is a huge hype around it, but it's not magic. At the end of the story, it's math. There is knowledge behind that. There is a lot of expert people working on this. So please don't trust this blindly, and at least try to understand what is behind as good as you can, because it's not magic. It's fun though, because this, again, I like to generate images working on this presentation, and I just input in I don't know if you know this, DALI is also created from the ChatGPT creators. It's really fun application to use. So for this image that you see, I just input that. Imagine what defeated by a calculator in a cartoon style. They just give me this. It's nice, come on. So that's all from my side. Thank you for your attention. I hope you have a nice time. I did. And if you have any questions, more research-oriented concerns, just don't hesitate to mail me or Professor W. We are open for everything, for discussion, collaborative research, etc. So thanks a lot. Yes. Sure. Which slide? Okay. Yes, so right. I will show you. So this is not done by me, as I said, because I wanted to use an open source data that everyone could download and everyone could manage. So what they did basically is to go to a workshop with the bearings and directly try to emulate some real faults that happen in real life. Okay, the drilling is not really happening in real life, but as also my colleagues can reassure this, in a lot of literature they induce outer race faults just by drilling a little hole in the outer race, which is very easy to implement, and that's why they do it. Another thing is like this electric discharge machining. In real life, this happens a lot with the so-called bearing currents. This high frequency current is like some discharges within the bearing, and it happens really like in both races and even in the rolling element it can happen, because at the end of the story it's a discharge. And in this case, okay, you need an accelerated lifetime test to really generate this in a realistic way. But what they did is just like that's a little cut. But from inside instead from outside, right?
So they implement
yeah, in a workshop. Yeah. And then, okay, also this pitting is coming from the same kind of phenomenon, this high frequency currents going through the bearing and discharging. So they did this just for emulating purposes, let's say. Of course, if you are more interested, it's available. You can download it and you can play with this data. And they have also the accelerated lifetime test data. And that's actually more interesting, but I wanted to keep it because it's way more tricky to explain, right? No problem.
Thanks for your presentation. Just for curiosity, do you know statistically, please, how dangerous the failure in experiments?
How dangerous?
How dangerous, how fast it happens. So you're losing the machine. What is happening actually?
So in my
besides the damage of the rollers inside the bells.
So in my own experience, it's critical. So if it fails, if it
critical to which sense?
That
it's 2 weeks critical.
That the shaft will go loose, right?
Or yeah, I understand, but it's 1 turn or 20 turns.
How long does it take?
Yeah, how long it takes?
If everything is okay, it will take very long. But
in failures of electrical machines, depends. For example, very well-known example is failure of flywheel. And in 1 turn, the damage of the composite material, so the whole composite material became just a powder, and flywheel was flying. Yes, it's very
in 1 turn.
It was very unpleasant accident at the company in the Netherlands, and 2 people were tremendously
injured.
Yeah, injured. One is the invalid for now, and actually all research about flywheels was stopped by many companies. Just 1 failure of experimental setup without understanding how fast the damage or this destruction or is happening. So this kind of fine work, but it would be interesting just for not only for curiosity, might be doing the introduction to down.
Okay, I take it. For example, in my own experience of research, I read a lot during my PhD thesis about this kind of like high frequency discharges in bearings. And there is some PhD thesis very interesting describing this phenomenon. But besides that, I didn't work with bearings that much. I am like in real life, only with this, what I was mentioning before, with this EBM discharging currents. I pretty much know the physics and know some models and so.
So the question was just, what is the lifetime before it becomes critical?
I think it really depends on the design. Design, application, environment, dust, no dust, temperature changes. I think it's really complex physics. So it's a big field. Yes, no problem. So I chose this way mainly because it has a lot of popularity in the research field. I mean, you have really like well-known papers about this, and as far as I know, it's applied. There are other ways, of course. We are here speaking about deep learning and image recognition, but there are more shallow ways to address this problem, right? You can just have your data, extract some statistical indicators, spin a neural network fully connected, right? I didn't do it here, but it's easier, definitely. Like easier in the way of like less algorithm complexity. Of course, definitive. Image. I don't agree. Okay. So you mean in like a guided way? Okay, like from the documentation point of view. Because if I think about it, if I have to implement it in an embedded system that uses memory and uses computational resources, I think it's way easier just to get the signal directly and just compute the statistics, shallow neural network, artificial neural network standard, and from there get this classification. Exactly. Okay. I didn't know because actually when I designed this like hands-on workshop, I tried to make it like good for people that don't know anything. Because I wanted to do something a bit more going in the deep learning side, because at the end of the story is a more novel technology than a shallow neural network. That's why. In the deep learning, could be, yes. Could be possible.
It's always a big debate whether you first have to get features and then work on the features, or you work on the raw data. And there is no conclusive answer.
It depends on the application. It depends why do you want to use it for. And of course, the deep learning, the magic of the deep learning is that you can use a more raw data. You don't need to work on the data. That's why it seems like magic, right? Because you just input data and then bam.
The less you know, the better you work with the raw data.
Yeah, that's
also know things you can use them more.
So it's really a creative task, actually, you think about it, like the whole process.
I have one question.
Yeah, sure.
Still on this topic, so did you read about somewhere to convert the signals to images? Because this is the one you might break up and everything will correct in life. Or the signal data into images.
So there is this.
Or does this mean that I can take any random data, convert it to images?
Well, it depends. I mean, sometimes it will not make sense, right? But for example, there is in the recommended reading that I showed here, exactly this article. One of the, not the first, before there were some other works, but this is one of the most cited, applied to the diagnosis, and they use a more fancy technique to convert data into images. But it actually had a huge acceptance. So that's why a lot of people now is trying to improve this, because I think even industrially also had a lot of acceptance. So that's why I went this way. And I think, I mean, for this data set, it worked.
For that, I would have talked with my research and saw that images also better.
Yeah, exactly right.
So you probably must have knew that you go further.
But as I said, this is not research. So this is something that I made out to easily explain and easily introduce people to use this kind of techniques. So if I will go into research, maybe I will do something different. So, first of all, I will do a deep state of the art.
Sometimes like exploration.
Yeah, exactly. Sorry, yeah? Sorry? With the pixels? You can play, but the thing is like one of the requirements that is pre-made and pre-trained architecture had is data size. So it really fixes it gives you already the dimensionality. Of course, I played with the resolution of time and frequency with the FTFT. And for some of them, it doesn't work. Yes.
And there they were always saying better resolution.
But also, I don't remember who mentioned before with the convolutional neural networks that it's up to a point, right? If you start inputting very big images, just imagine the complexity. Like at the end of the story, you end up with like endless amount of layers, endless. It will become, in my head, it will become very, very complex. So at the end of the story, as I said, this is the trade-off that I found interesting to start with this. But of course, as we said with Raluca, it's just really think about it's quite creative. Trial and error, right?
I have one more from slide.
No problem.
Can you go to slide 5?
Yes.
If you are a manager, which
It depends on the available capital, I guess. If you have a small company, definitively. But I don't have so much experience with this. But for example, Professor Antonino, he works in the field many years, and he even does industrial visits, industrial courses to some big customers in Germany, in other countries, where they have a very, very large fleet of motors. And definitively, there is a lot of interest on this, like more fancy kind of maintenance, because at the end, there is a lot of money that you lose because of like periodic maintenance. So it's really a concept on maintenance engineering. If I have 2 motors, maybe I don't care so much. But if I have 20,000, or a very big one, that is very expensive.